how we're doing it. And Mrs. Claus sent me over here to get more cocoa and peppermint sticks because I'm gonna be working late in the next couple of days. I'm glad they were gone when I got my stuff and left because I bought neither cocoa nor peppermint sticks. But it made me feel good to bring the little boy some joy.
Good. Okay, we're gonna talk about active circuits. Basically, in this, we're gonna talk about analog devices, vacuum tubes, semiconductors, diodes. When we use a diode as a rectifier, and then get into transistors, bipolar, and field effect. Probably none of us can actually explain the physics of a field effect transistor, so I'm not going to try. Just take it on faith, they work. Oh, what, did you get a good one?
Cinnamon.
Oh, yeah, those are. Okay, vacuum tubes. Don't recall if there's anything on the technician test, but they do show up still on the general and the extra because vacuum tubes are still around. We haven't found a cost-effective replacement for high power devices. So broadcast radio and TV is still using tubes.
Okay.
Big expensive tubes. Even amateur radio power amplifiers are still both tube and solid state. In fact, I just recently procured one at the Hamfest.
Solid state.
No, tubes. I like tubes. They glow.
I have one tubes.
Did I send you that video of the guy that built the tube audio amplifier? An old 1920,
I think you did.
and he made his own tubes.
I didn't see that
I
part of
didn't
it.
see that.
Oh, that is hardcore. You gotta watch that. And, I mean, he knew what he was doing. I mean, he explained all the whole 9 yards.
Getter in there.
The getter and all that stuff. Okay, so this guy Guthrie, which probably you never heard of, I hadn't actually sort of discovered thermionic emission. Thomas Edison was kind of enthralled with it, and he called it the Edison effect because he liked to name things after himself, even though somebody else actually discovered it. But what his effect was, if you had a heated element in a vacuum tube and a anode or another contact, that as you applied a voltage to it and heated the filament, you could control the amount of current flow by varying the amount of current on the filament. In other words, varying the heat. And that's what he explored as maybe some way to modulate or control the current flow, which turns out isn't actually very useful, but he seemed to think it was. In 1904, and I guess this was still in Edison's time, this guy Fleming used the, in essence, rectifying effect, the fact that current would only flow from the heated filament up to the anode, not in the reverse direction. So it effectively was a diode before they knew what a diode was. And he was able to use it as a detector for radio signals, which I'm not exactly what they used prior to that. It says magnetic, but I'm not sure what that
Whisker.
was. Huh?
Cat's whisker.
Well, yeah, they did use those, but that's really a solid state semiconductor. Cats,
Well, they
yeah,
used to-
wire on a galena crystal.
Oh, I didn't realize that.
I have a chart.
Oh. I'm not old like you. I don't remember any of that.
Okay, so it turns out the simplest vacuum tube was the diode or the Fleming valve, which they called it. It just had a heated cathode and an anode, and it would conduct current. And the conventional current would go from the anode to cathode, but actually it was electrons that were energized by the heat. And you had an electron cloud around the cathode, and when you applied a high voltage on the anode, it would attract the electrons.
Actually, they made, they call them rectifiers, you know. I remember we used to have rectifiers used to make the high voltage.
Oh, yeah. Yeah, I used to, in high school, repair car radios for this used car guy.
Yeah,
And a lot of the older cars would have a vibrator
right.
and a vacuum tube rectifier in order to get the voltage up. Those were easier to work on. All you had to do was figure out which tube was bad.
Yeah, they usually didn't light up, you'd pull it out, and put a new one in.
Solid state's not that easy. Okay, so the main thing about the diode is electrons only flow in one direction. Now that's true whether or not it's a vacuum tube diode or a semiconductor diode, which we'll talk about in a little bit. So Audion, which I thought I had his name on there, I forgot his first name, discovered that if you added a grid between the cathode and the anode that you applied a potential to, and it could be a small voltage, it created a field which would block the electron flow between the cathode and the anode. So by varying a small voltage on the grid, you could control the amount of current through the tube between the anode and cathode. And we call those triodes. Later, they added additional grids for different purposes to improve it. And we call them tetrodes and pentodes, where a pentode had 3 grids, a cathode and an anode, so it was 5. This is kind of a picture of a simple diode, where you've got a filament heating up the cathode and it's surrounded by an anode, or we call it a plate, and it's all in a vacuum. And you heat up all these electrons and create this little electron cloud, and then they get attracted over to the plate. And at a certain point, these kind of get a nice cherry red color, which are pretty. Over here is the same basic tube with a grid added. And a lot of times, these grids don't have to be like a screen mesh. They're various forms. You could just be wire around there. In the video of the guy that built his tubes from scratch, it was just a coil of wire he used as a grid.
And there's a potential on the grid.
There's a potential on the grid that at 0, it's a diode.
Right.
It passes current. The higher the voltage on the grid, it creates a field that blocks the current flow.
Right.
So at a certain grid voltage, you'd get to cutoff and you'd have zero current. And it's fairly linear.
Right.
This is just a schematic of a simple triode tube. And where we're emitting free electrons from the cathode to the anode. So we have conventional current going anode to cathode. This is just a picture of a lot of different typical tubes.
6146.
After watching that video, and he's got several more on doing tubes and stuff, it kind of got me the urge of making a tube amplifier. Until I priced the tubes.
Yeah, I'm not looking,
Tubes aren't just out of sight.
I've got an old console tube radio at home, and it's got a phonograph on it and everything too, and it's got the little thing on there, you have to watch it until it glows. But I've never plugged it in, and that's gonna be one of my retirement projects, is trying to get that thing back up and running, because sound is so much better.
Oh,
when it
it's
comes from
definitely,
tubes.
well, it's colored sound,
Mhm.
but it does sound better, which is why all the musicians use tube
Oh, yeah, tube
amplifiers
amps, yeah.
because of the distortion.
And they're going back to vinyl records now too.
Oh, really?
They are, well, they've
Wow.
never stopped producing them, but they're producing more now than they have in probably the last 20 years.
Yeah,
25
especially
years.
in Europe.
Yeah,
This is a typical RF power amplifier that uses tubes, still made today. It's very similar. I think this is an 811. Mine's an 811H. I've got 4 tubes. This only has 3. Okay, so we went from vacuum tubes to solid state. And one of the first solid state
That was my cat's whisper.
semiconductors turned out to be what we call a cat's whisker detector. It's a piece of galena, which is a lead sulfide crystal. And you attach I'm not sure it's actually attached, but there's a fine wire that contacts the crystal. And it acts as a diode. So it was able to detect or rectify amplitude modulated signals. It's just like, and we'll talk about it in a little bit on the diodes. I keep forgetting to turn mail off. You're just rectifying the high frequency out and just seeing the envelope of the waveform.
Isn't silicon is most common now? Before it was germanium, wasn't it?
They used germanium,
Was the first one used.
not too much today.
Yeah.
I'm not exactly sure. One of the things, germanium is good for cases where you care about the threshold voltage, because it's 0.3 volts as opposed to 0.7 volts for silicon. For high frequency stuff, they're pretty much using gallium arsenide. Not a technician question, but it is on the extra.
Oh, okay.
So today we make semiconductors basically from silicon. You have intrinsic silicon, which is just pure silicon crystals. And that's usually used as a base for a semiconductor. or an integrated circuit where you have lots of semiconductors on this common silicon substrate. Because pure silicon is kind of an insulator. It's called a semiconductor because it's in between a metal and an insulator, because it has 4 valence electrons. And it also has this interesting habit. A metal, when you heat it, increases its resistance to current flow, which is how a light bulb filament works. When it's cold, it's very low resistance. As you apply a voltage and current, it heats it up, and the resistance of the filament increases until you reach a steady state point. Silicon is just the opposite. As you heat it, its resistance decreases, which is why in solid state devices like solid state power amplifiers, you have a thing called thermal runaway because of that effect. Because as it heats up, it lowers its resistance, which increases the current flow, which increases the heat, which
The constant current generator used.
So
Light bulbs.
basically all solid state stuff, except for high frequency or very special cases, is made from silicon, either pure silicon or what we call extrinsic material, which has been doped. In other words, we add an impurity to make it a positive or a negative charged material. So if we look at a silicon crystal, you see all these little silicon atoms with 4 valence electrons, and they tend to pair up with other silicon atoms. And we have these they call covalent bonds, where they share the shell. In this case, to make an N-type material, we added a phosphorus atom. And when those get injected into the crystal, and we won't talk about how they do that, there's different diffusion methods and stuff, but anyway, they get phosphorus atoms in there, and a phosphorus atom has 5 valence electrons. So we wind up, when they all pair up, we got an extra electron around here. It's like musical chairs. You take a chair away and the guy's got no place to sit. So it becomes negatively charged material. It's got excess of electrons. If we take and add boron, which is the other most common impurity, and boron only has 3 electrons in its valence shell, we wind up with a hole. So we wind up with a positively charged material because it's got a hole or a place for a free electron to go. And this is just showing the different energy levels. And you see this gap between the conduction band and the valence band, which are energy levels, where we had a metal, when we saw that the last time, the conduction and the valence band overlapped. So there was no voltage threshold required to move from the valence to the conduction band for those electrons to move. In the case of the semiconductor materials, there's a band gap. So it takes energy to get it from here to there, which is what creates that 0.7 volt threshold voltage in order for current to flow through a semiconductor junction. Right. So the simplest semiconductor, like the simplest vacuum tube, is a diode. And it's made from a junction of a P-type and N-type silicon. So we take those 2 doped pieces and put them together. Actually, in some cases, they sort of grow them together. And that junction acts like the vacuum tube diode, and it'll only pass current in one direction, from the P to the N, anode to cathode. But which actually means the electrons are moving from the cathode to the anode, and the holes, which are virtually moving, are going from the anode to the cathode. And we call that forward biasing, okay, when there's a higher potential on the anode to the cathode. Here I did a little plot of a typical 1N4001, which is a 1 amp diode, very, very common. And in this simulator, they also have a perfect diode. So I plotted the two of those. And in the case of the perfect diode, at 0 volts, okay, and above, it starts to conduct current. And the slope of that line is limited by the series 10 ohm resistor. In the case of the silicon diode, if we come out here, it's approximately somewhere between 0.6 and 0.7 volts where that knee is, and it starts to conduct. And then it goes up almost the same slope because it's got a 10 ohm series resistor. But if you look closely, it's not exactly parallel because there's some internal resistance in the diode. We call ohmic resistance, which is why it's slightly lower slope, which means it's maybe 11 ohms total instead of 10.
Like 0.7 volts between the two lines.
Yeah. Except for the loss.
Yeah.
This chart just shows a lot of the different diodes. There are some questions on the tech exam to identify the types. So they will show you the symbol and you have to identify what it is. So a standard diode is a filled-in triangle going into a bar that represents the cathode. The triangle represents the anode. And you can't really see it because the watermark thing covers it up. But there's a white stripe on this end, which is how they're normally marked, so you know which is the cathode end. You can see it more on this one with a black stripe over here because it's a clear, it's like a glass coating. And it's a Zener diode, and it's represented with what looks like a Z for the cathode. The interesting thing about Zener diodes is you use them in reverse polarity, and they have a controlled breakdown voltage where it will conduct at a specific, in reverse direction at a specific voltage. So if you get a 5-volt Zener and you put a resistor in series with it reverse, it will act as a voltage regulator basically, and you could generate a 5-volt reference source just with a resistor and a Zener diode. We have a Schottky diode, which this thing kind of looks like an S, named after one of the, well, he wasn't a transistor inventor. He was a, because that was Shockley. I'm not sure what Schottky did, but a different guy.
I thought it was the high frequency diode.
Thought what?
Very high frequency.
What?
The Schottky.
No, it has a lower threshold.
Okay.
Well, and it also has lower capacitance, so it's higher frequency.
Yeah.
But it's basically because of the lower threshold voltage.
Oh, okay.
You have tunnel diodes, which are used for high frequency stuff, and I don't know a whole lot about them. I've never used them much.
They used them as oscillators somehow. I don't know
Yeah,
how it works.
right. you could make a little oscillator with a tunnel diode and a capacitor.
But I never used one to know how it worked.
I don't, that one won't be on the exam. I'm pretty sure.
I don't remember.
Light emitting diodes are very popular. That will be. It looks like a regular diode, but it's got a couple little arrows representing the light being
We use those all over the place.
generated.
Lights now.
Oh, now, yeah. There aren't any pilot lights or anything anymore like we used to have. You have a photodiode and you see the arrows go in the opposite direction, which means the light comes into the diode and causes it to conduct, as opposed to the light emitting diode, which emits light. Now, it turns out, not on the exam, but all PN junctions generate light to some extent. So for a light emitting diode, they've used different materials to increase the effect, and they put them in clear packages so the light can get out. But if you had a regular diode in a clear package, it would emit light. And it also, when receives light, would act like a photodiode.
Mhm.
And you do the same thing with a transistor. If a phototransistor has a clear section on the top of the case, so light can get to the junction and act just like a voltage on the base. Laser diodes won't be on the exam, and I've never figured out what a current regulator diode is, and I never wanted to look it up. Varactor diode, possibly, I think is. And a varactor diode is basically a standard diode used in reverse fashion. And it turns out that the PN junction between the two materials acts like a capacitor. And as you apply a reverse bias voltage, it affects the depletion zone and basically the effective capacitance of that junction. So by applying a varying voltage, you can vary the capacitance. So they use those as a variable capacitor that's electrically controlled. You hardly ever see the old variable capacitors with the plates that mesh. And if you can find one, they're extremely expensive, but they're almost never used anymore. Okay, so we have a diode, and one of the main things is we can use it to convert AC to DC. We call it rectification. The little circuit I drew here was just a simple transformer with AC coming in through the switch and a diode on the output feeding a 100 ohm resistor. So if we look at the plot for that, okay, we have a primary voltage here of about 12 volts, and we have a secondary voltage of about 24 volts on the positive peak. But you notice on the negative peak, we had 0 because the diode only passes voltage in one direction. We call that a half-wave rectifier because it only rectifies half of the waveform. Now we have a full-wave rectifier. This thing always seems to be in the way. Almost the same circuit, except here we have a center tap transformer and 2 diodes. So we're going to conduct on each half of the cycle. And in order to get the same voltage, and I've got like twice the windings here. So if you look at this one, the primary voltage is up around 12 volts. What we're seeing out of the secondary is 12 volts minus the voltage drop across the diode. On the negative cycle, okay, we're rectifying that through the other diode, and it's also going to be 0.7 volts less than the primary. So we call that a full wave because we're rectifying the entire waveform. So we're going to get, if this was 60 cycles, for instance, we'd have 120 pulses per second of pulsing DC instead of 60. We can do the same thing with what we call a bridge rectifier, which you can buy, and it's just 4 diodes connected together in a single package. So you get the same effect as a full wave rectifier. It doesn't require a center tap transformer. So in some cases, manufacturing wise or cost wise, it might be cheaper. One of the differences you'll see, there's a bigger gap because there's a 2 diode drop for each of these. So it's going to be 1.4 volts less than the primary. Okay, any questions on those things?
I'm good.
Okay. Where's my stop?